In this video, I want to cover several topics that are all related. And on some level, they're really simple, but on a whole other level, they tend to confuse people a lot. So hopefully we can make some headway. So a good place to start, let's just imagine that I have some type of container here. Let's say that's my container. And inside of that container, I have a bunch of water molecules. It's just got a bunch of water molecules. They're all rubbing against each other. It's in its liquid form. This is liquid water. And then inside of the water molecules, I have some sugar molecules. Maybe I'll do sugar in this pink color. So I have a bunch of sugar molecules right here. I have many, many more water molecules, though. I want to make that clear. I have many, many more water molecules in this container we're dealing with. Now, in this type of situation, we call the thing that there's more of, the solvent. So in this case, there's more water molecules, and you can literally just view more as the number of molecules. Now, I'm not going to go into a whole discussion of moles and all of that, because you may or may not have been exposed to that yet. But just imagine whatever there's more of, that's what we're going to call the solvent. So in this case, water is the solvent. And whatever there is less of, so the more, water is the solvent, and in this case, that is the sugar, that is considered the solute. This is the solute. So the sugar, it doesn't have to be sugar. It could be any molecule that there's less of than the water in this case. Sugar is the solute. And we say that the sugar has been dissolved into the water. Sugar has been dissolved into the water. And this whole thing right here, the combination of the water and the sugar molecules, we call a solution. We call this whole thing a solution. And a solution has a solvent and a solute. The solvent is water. That's the thing doing the dissolving. And the thing that is dissolved is the sugar. That's the solute. Now, all of this may or may not be review for you, but I'm doing it for a reason, because I want to talk about the idea of diffusion. Diffusion. And the idea is actually pretty straightforward. If I have, we'll say the same container. Let me do a slightly different container here, just to talk about diffusion. We'll go back to water and sugar, especially back to water. But let's say we have a container here. And let's say it just has some air particles in it. It could be anything, oxygen or carbon dioxide. So let me just draw a couple of air molecules here. So let's say that is a gaseous, just for the sake of argument, gaseous oxygen. So each of this is an O2, each of those, right? And let's say that this is the current configuration, that all of this is a vacuum here, and that there's some temperature. So these water molecules, they have some type of kinetic energy. They're moving in some type of random directions right there. So my question is, what is going to happen? What is going to happen in this type of container? Well, any of these guys are going to be randomly bumping into each other. They're more likely to bump into things in this down left direction than they are in the up right direction. So if this guy was happening to go in this down left direction, he's going to bump into something and then ricochet into the up right direction. But in the up right direction, there's nothing to bounce into. So in general, everything is moving in random directions, but you're more likely to be able to move in the rightward direction. When you go to the left, you're more likely to bump into something. So it's almost common sense. Over time, if you just let this system come to some type of equilibrium, and I'm not going to go into detail on what that means. You can watch the thermodynamics videos if you'd like to see that. You'll eventually see the container will look something like this. I can't guarantee it. There's some probability it would actually stay like this, but very likely that those 5 particles are going to get relatively spread out. This is diffusion. And so it's really just the spreading of particles or molecules from high concentration to low concentration areas. Right? In this case, the molecules are going to spread in that direction, from a high concentration to low concentration area. Now you're saying, Sal, what is concentration? And there's many ways to measure concentration, and you can go into molarity and molality and all of that. But the very simple idea is how much of that particle do you have per unit space. So here you have a lot of those particles per unit space, and here you have very few of those particles per unit space. So this is a high concentration, and that's a low concentration. So you can imagine other experiments like this. You could imagine a solution like, let's do something like this. Let's say I have two containers. Let's say two containers. Let's go back to the solution situation. So this was a gas, but I started off with that example. So let's stay with that example. Let's say that I have a door right there that's larger than either the water or the sugar molecules. On either side, I have a bunch of water molecules. I have a bunch of water molecules on either side, just like that. On either side. So I have a lot of water molecules. So if I just had water molecules here, they're all bouncing around in random directions. And so the odds of a water molecule going this way equivalent to odds of a water molecule going that way, assuming that both sides have the same level of water molecule. Otherwise, the pressures would be different. But let's say that the top of this is the same as the top of this. So there's no more pressure going in one direction or another. So if for whatever reason a bunch more water molecules were going in the rightward direction, then all of a sudden this would fill up with more water, and we know that isn't likely to occur. So this is, this is just a solution or this is just a kind of two containers of water. Now let's put some solute in it. Let's dissolve some solute in it. And let's say we do all the dissolving on the left-hand side. So we put some sugar molecules on the left-hand side. And these are small enough to fit through this little pipe. That's one assumption that I'm making. So what's going to happen? All of these things have some type of kinetic energy. They're all bouncing around. Well, over time, the water is going back and forth. This water molecule might go that way, that water molecule might go that way, but they net each other out. But over time, one of these big sugar molecules will be going in just the right direction to go through. Maybe this guy, instead of going in that direction, he starts off going in that direction. He goes just through this tunnel connecting the two containers, and he'll end up there, right? And this guy will still be bouncing around. There's some probability he goes back, but there's still more particles, more sugar particles here than there. So still there's more probability that so this guy's on that side, so let me cross him out. But there's still more probability that one of these guys will go to that side than one of these guys will go to that side. So you can imagine if you're doing this with gazillions of particles, I'm only doing it with 4, over time, the particles will have spread out so that their concentrations are roughly equal. So that, maybe you'll have 2 here over time. But if you're, when you're only dealing with 3 or 4 or 5 particles, there's some probability it doesn't happen. But when you're doing it with a gazillion and they're super small, it's a very, very, very high likelihood. But anyway, this whole process, we went from a container of high concentration to a container of low concentration, and the particles would have spread from the low concentration container to the high concentration container. So they diffused. This is diffusion. This is diffusion. And just so that we learn some other words that tend to be used with the idea of diffusion, when we started off, this had a higher concentration. The left-hand side container had higher concentration. Higher concentration. Higher concentration. It's all relative, right? It's all higher than this guy. Higher concentration. And this right here had a lower concentration. Lower concentration. And there are words for these things. This solution with a high concentration is called a hypertonic solution. Let me write that in yellow. Hypertonic solution. Hyper, in general, meaning having a lot of something, having too much of something. And this lower concentration is hypotonic solution. Lower concentration. You might have heard maybe one of your relatives, if they haven't had a meal in a while, say, "I'm hypoglycemic." That means that they're feeling lightheaded. There's not enough sugar in their bloodstream, and they want to pass out, so they want a meal. If you just had a candy bar, maybe you're hyperglycemic, or maybe you're just hyper in general. But so these are just good prefixes to know, but hypertonic, you have a lot of the solute, so you have high concentration. And then in hypotonic, not too much of the solute, so you have a low concentration. These are good words to know. So in general, diffusion, if there's no barriers to the diffusion, like we had here, you will have the solute go from a high concentration or hypertonic solution, if they can travel, to a hypotonic solution, to a hypo where the concentration is lower. Now, let's do an interesting experiment here. We've talked about diffusion, and so far we've been talking about the diffusion of the solute, right? And in general, and this is not always the case, if you want to be as general as possible, the solute is whatever you have less of. The solvent is whatever you have more of. And the most common solvent tends to be water. But it doesn't have to be water. It could be some type of alcohol. It could be it could be mercury. It could be a whole set of molecules. But water in most biological or chemical systems tends to be the most typical solvent. It's what other things are dissolved into. But what happens if we have a tunnel where the solute is too big to travel, but water is small enough to travel? So let's think about that situation. Let's think about that situation. In order to think about it, I'm going to do something interesting. Let's say we have a container here. Let's say we have, actually, I won't even draw a container. Let's just say we have an outside environment that has a bunch of water. This is the outside environment. And then you have some type of membrane. You have some type of membrane here. That's a membrane. Water can go in and out of this membrane. So it's semi-permeable. Well, it's permeable to water, but the solute cannot go through the membrane. So let's say that the solute is sugar. So we have water on the outside and also inside the membrane. So these are little small water molecules. This is a membrane right here. And let's say that we have some sugar molecules again. I'm just picking on sugar. It could have been anything. So we have some sugar molecules here that are just a little bit bigger, or they could be a lot bigger. Actually, they're a lot bigger than water molecules. So you have a bunch of, and I only draw 4, but you have a gazillion of them, right? But you have that much more water molecules. I'm just trying to show you have more water molecules than sugar molecules. And this membrane is semi-permeable. Semi-permeable. Permeable means that it allows things to pass. Semi-permeable means it's not completely permeable. So semi-permeable in this context, I'm saying I allow water to pass through the membrane. So water can pass. Water can pass. But sugar cannot. Sugar is too large. Sugar cannot. And the reason why in this case is because the sugar molecule is too big. So if we were to zoom in on the actual membrane itself, maybe the membrane looks like this. I'm going to zoom in on this membrane. So I'm going to zoom in on this membrane. So it has little holes in the membrane, just like that. And maybe the water molecules are about that size, so they can go through those holes. So the water molecules can go back and forth through the holes, just like that. But the sugar molecules are about that big, so they cannot go through that hole. They're too big for this opening right here to go back and forth between them. Now, what do you think is going to happen in this situation? So first of all, let's use our terminology. Remember, sugar is our solute, water is our solvent, semi-permeable membrane. Which side of the membrane has a higher or lower concentration of solute? Well, the inside does. The inside is hypertonic. Hypertonic. So I could write here, hypertonic. The outside has a lower concentration, so it's hypotonic. It's hypotonic out here. Lower concentration of solute. Now, if these openings were big enough, based on what we just talked about, these guys are bouncing around. Water is traveling in either direction and equal probability, or I'm going to talk about that in a second. If everything was wide open, it would be equal probability. But if it was wide open, these guys eventually would bounce their ways over to this side, and you would probably end up with equal concentrations eventually. And so you would have your traditional diffusion, where high concentration of solute to low concentration of solute. But in this case, these guys, they can't fit through the hole. Only water can go back and forth. If these guys were not here, water would have an equal likelihood of going in this direction as they would be going in that direction. A completely equal likelihood. But because these guys are on the right-hand side of, or in this case, on the inside of our membrane, this is our inside of our membrane zoomed up, these guys, it's less likely, because these guys might be in the kind of the approach position of the holes, it's that slightly less likely for water to be in the approach position for the holes. So it's actually more probable that water could enter than water exit. And I want to make that very clear. If these sugar molecules were not here, obviously it's equally likely for water to go in either directions. Now that these sugar molecules are there, these sugar molecules might be on the right-hand side. They might be blocking, I guess the best way to think about it is blocking the approach to the hole. They'll never be able to go through the hole themselves, and they might not even be blocking the hole, but they're going in some random direction. So if a water molecule was approaching, it's all probabilistic, and we're dealing with gazillions of molecules. It's that much more likely to be blocked to get outside. But the water molecules from the outside, there's nothing blocking them to get in. So you're going to have a flow of water inside. So in this situation, with a semi-permeable membrane, you're going to have water. You're going to have a net inward flow of water. And so this is kind of interesting. We have the solvent flowing from a hypotonic situation to a hypertonic solution. But it's only hypotonic in the solute. That's when you talk about the solute. And it's only hypertonic when you talk about the solute. But water, if you flip it the other way, if you view sugar as the solvent, then you could say we're going from a high concentration of water to a low concentration of water. I don't want to confuse you too much. This is what tends to confuse people. But just think about what's going to happen. No matter what, in what situation, the solution is going to do what it can to try to equilibrate the concentration, to make the concentrations on both sides as close as possible. And it's not just some magic. It's not like the solution knows. It's all based on probabilities and these things bumping around. But in this situation, water is more likely to flow into the container. So it's actually going to go from the hypotonic side, when we talk about it, low concentration of solute, to the side that has high concentrations of solute, of sugar. And actually, if this thing is stretchable, more water will keep flowing in, and this membrane will stretch out. But we won't go into too much detail here. But this idea of water, of the solvent, if in this case water is the solvent, of water as a solvent diffusing through a semi-permeable membrane, this is called osmosis. Osmosis. You've probably heard learning by osmosis. If you put a book against your head, maybe it'll just seep into your brain. Same idea. That's where the word comes from. This idea of water seeping through membranes to try to make concentrations more equal. So if you say, well, you have high concentration here, low concentration here. If there was no membrane here, these big molecules would exit. But because there's this semi-permeable membrane here, they can't. So the system, just probabilistically, no magic here, more water will enter to try to equilibrate the concentration. And eventually, if maybe there's a few molecules out here, not as high concentration here. Eventually, if everything was allowed to happen fully, you'll get to the point where you have just as high a concentration on this side as you have on the right-hand side, because this right-hand side is going to fill with water and also probably become a larger volume. And then once again, the probabilities of a water molecule going to the right and to the left will be the same, and you'll get to some type of equilibrium. But I want to make it very clear. Diffusion is the idea of any particle going from higher concentration and spreading into a region that has a lower concentration and kind of just spreading out. Osmosis is the diffusion of water. And usually you're talking about the diffusion of water as a solvent. And usually it's in the context of a semi-permeable membrane, where the actual solute cannot travel through the membrane. Anyway, hopefully you found that useful and not completely confusing.